Good evening. Can you hear my voice okay? I want to start desktop sharing. Okay, can you see the desktop? Let's see, good evening, Albert, Cynthia, Karen, Mega, welcome. Daniel, welcome. First, are there any questions before we begin? Thank you, Cynthia. Okay. Well, if you do, just go ahead and type one in and I'll stop and listen. Were there any questions on Chapter 14? No, Chapter 14 is next week, I think. Let me check that. Yeah, 14 and 15 are next week. I forgot to take that off the agenda. So we're not going to discuss that tonight. I'll answer the CC Confer question in a little bit. Regarding the final exam questions, I finally figured out what went wrong. The chapter to students for final exam questions has been corrected. What I found was Canvas has a bug displaying text files that have numbers at the beginning of each line. So what I ended up doing was putting CHP in front of the numbers so it wouldn't keep adding numbers when it displayed it. So now it'll display it correctly. So you can take a look and find out what chapter you were assigned to. Okay, that's right here somewhere. That link. Right here. That's this link. Okay. Speaking of the questions, let's take a look at this discussion of how I want the format. I already got a question and I replied. Okay. So you just read all that so you can understand what I'm trying to say. This example that I did didn't have the A through E. Either way would be fine, as long as your answers are on a separate line. I think when it goes in, it takes that off anyway. So if you use this format or this format, it should be fine. Let me think. I would avoid it if you can, Karen. I believe you can attach, maybe I didn't set that up or allow it, attach images. Yeah, I don't see on the reply the capability. I just replied to King's question. So what you might want to do is if you have an image You could email me the image and then say in your question, see image, and I'll try to add it to the question. Yeah, you could try that, sure. Any other questions about what I'm expecting? 3 questions in the format, the way I indicated it. The main things are your questions need to be separated by spaces, a line. Your answers have to be on each separate line, and they start no empty space or lines between your question and your answers. And you have a starting brace and an ending brace. And if you put, chap and 2-digit number, your first name, and the question, I think that'll flow in nicely. And you indicate the correct answer by putting an equal in front, and the incorrect answers are using tildes. And you've got 14 days to get it to me, your 3 questions for your chapters. Once again, if I don't get chapter questions for a specific chapter, you'll get my questions and you won't be able to see them, okay, because you won't be able to see them. Let's see. Let's go back to the site. I'm going to do the anecdotals first because the CC Confer question refers to the anecdotals. And then we'll spend the rest of the time reviewing for the tests. How does that sound? Okay. Welcome, Kang. I just have some notes that NFS used to be stateless. The World Wide Web is stateless, and the idea of having states was at the server side. So when you're on a session on a server, it keeps your state. So things like the Internet system, the III system, if you have Microsoft web service, or you could have PHP type sessions. So a lot of things are stateless. You have to kind of keep the state somewhere within the server. Basic rights network file servers. This goes back many years ago because when I was at Syntax, I put in the first LAN, local area network. They didn't have Ethernet at that time. TCP/IP wasn't yet thought of being a great thing, but the IBM had a star network. You had this huge cable. I mean, it had to be 3/4 of an inch thick, that you would go from your file server to your various workstations. And NetWare was the software that ran on those networks. And that's what I installed, Network 1A. It was really fun. You had 8 basic rights, and they've basically you have these same 8, but they've added a ton of others. But you have the right to create a file or directory, delete one, read, write, update, or execute. And there were some special rights for owner's rights kind of concept. And you establish groups. For example, in your file server, in this mechanism, you would assign the finance group read and write access to their specific directories. And then the management group, you might assign read only so that the president, vice president could read the finance files, but not be able to update them. Things of that nature. And then over the years, the capability increased to now what we have in Microsoft is the Active Directory for the enterprise, and then we have domain servers underneath it. And the domain servers came from this server concept back in the 80s. LDAP program API to access this security scheme. Lightweight Data Access Protocol would be this. This is what LDAP stood for, or Local Data Access Protocol. Mainframe. Okay, here's our first kind of experience here. Mainframe had problem with buffers. The IBM 36370 architecture, 1980s, was the program status word. That's what this stood for, program status word. It had a virtual storage address and a user and a supervisor mode. User mode was, I believe, a 1 or a 0. I can't remember now. I think user was 0 and supervisor was 1, or vice versa. But in that mode, you could do anything. You could run any instruction in the supervisor mode. You had control bits, flags for 24-bit, or flag 1 for 32-bit. So this flag kind of told you, are you executing a 24-bit instruction or a 32-bit instruction? There's something like this on the test, so I want you to understand. If I have a segment of 4 bits, I can have 16 segments. If I'm doing a 24-bit thing, I could have 16 segments, 2 to the 4. Within each segment, I could have 256 pages. Within each page, I could have 12 bits or 4K displacement. And if you added the 12, the 8, and the 4, you get 24 bits. And for a long time, the system ran on 24-bit instruction set. The extended architecture was 32 bits. So it doubled the number of segments, and it made a half more the number of pages that you can have in a segment, but there's still 4K size displacement or page frames with that. And I posted this on, not that one, I posted this on Canvas. This is the IBM 370 reference card. I love these reference cards. I have several of these. This I happened to pull off the internet. Somebody copied it. But it kind of explains all of that. And what was kind of interesting, you see the different formats for the instructions, whether it's a 1-byte instruction, a 2-byte or a 2-word instruction, or a 3-word instruction. Depends on the length of the instruction. Okay? And then each of these, of course, have the different opcodes. and what they do, and I thought one would be interesting to share with you, and that was this one here. TS is the test and set instruction, and we talked about that instruction to create locks, and that's how you would do it with this test and set instruction. So the other thing is, let me look down here. These are all the opcodes and the mnemonic, okay, because it's all in binary. So this would be the actual instruction code in binary and what it would mean. And then there's the fixed storage locations in memory. We talked about that. So this has in these area, it saves the running program counter and puts in the new program counter, and the hardware interrupt scheme does that. Okay? Like this one says, this one here is the external. Let me make it a little bit, I guess it get much bigger. See, on the restart, it's got the old PSW and the new one. So each of the different types of interrupts, it would store the saved one, and then that would be load the new one. And we talked about that. So some of this stuff we talked about. Here's a program status, a PSW word, and they're in different modes. Basic core mode versus extended mode. All right, and then there were the various interrupt codes that could happen. Okay. So with that in mind, let's talk about this. So the architecture was 24 bits. And IBM extended the ability of the operating system to go to 32 bits. And what you had to do was you had to recompile all the OS programs required to implement this. So we went to the 32-bit, and for periodically, what happened after this was periodically the OS would die. It would just stop working. And it was random, once or twice a week. And they just rebooted and would run for a while. This happened for about 2 months. We had IBM come in on the 3rd month, IBM, and they were sitting watching the console and watching the console addresses that are coming on the console to see what the heck was going on here. Now you need to understand what's happening in the operating system. The spooler we've talked about. The spooler spools the disk, it spools the printer, it spools the card reader, and it uses the producer-consumer concept where, you know, if I want to print something, I spool that from my program, or if I want to read data in, I would spool it from card or spool it from disk. Okay? See, so far so good. IBM Disk Controller, okay? They had a special controller. When it wrote to the disk, it left any bad data on it, on that sector, and made a note somewhere else on the disk that needed to be corrected. So that specific block needed to be corrected, so the correction program that took the bad block from the data to the disk and corrected it in memory. It was a small little routine. The issue was that the correction program wasn't compiled for the extended addresses. And it was zapping memory locations that were in the spooler itself. So if the spooler goes down, how could any work get loaded into the master scheduler? So it was causing that problem. When it tried the correcting program, tried to fix the blocks, it was fixing the blocks not in the right buffer where the file was reading them, but in the spooler program itself. It was zapping it. And it took them, like I said, a whole month to figure that out. When our system guys got the list from IBM to recompile, this guy wasn't on it. The correction program, IBM missed that. Because it's such a small little routine, it's kind of probably a utility routine in their minds, but it was important because it was using different addresses. It was using the 24-bit addresses, so it was going to the wrong place in memory. Is that clear for you guys, that problem? Good. Okay, another example about the way things used to be is the operators had a big console, and there was a big red push button in case of emergency. And they smoked in the room. They allowed them to smoke in the room. And a lot of the old listings of paper were put in these huge round bins. One of the bins caught fire. The new operator pushed the big red button. Okay, what it does is it drops a protective box down over the CPU, because that's the most valuable part of the computing. And when it drops this box, as IBM designed it, all the connections to the CPU are cut, because it's dropping them right on the address lines, on the processor board. Well, it takes about 3 days to replace the motherboard and set it up again. So you shouldn't press that button unless it's a real, serious emergency. There's another story, and there's other stories. Let's go to our CC Confer question of the week. Preview it. Okay, what was the name of the part of the OS system that had the issue Art talked about Thursday evening? What was it, the part of the operating system that I talked about in this one? Yeah, without the question mark. I'm going to submit it, check it, make sure it works. I did this earlier, so I know it'll work. Yeah, correct. I got it. I passed my test. Okay. We did that. Any questions so far? Then I'll start the review. Okay, we covered, let me put the notes here. We covered real memory management, real memory and its management. Do you recall the various types of real memory and allocating them? Fixed size partitions. In other words, each partition has a specifically fixed size, and we place the program in the appropriate size, and of course the remaining of that size is fragmentation. That's one side. Variable size partitions. We take a partition and we stick a program in it, and it has a remaining hole that we might put another program in. Okay, in this one, in the variable size partition concept, we had three mechanisms of putting programs in the holes. Remember, they created holes. The were A, first bit, best bit, and worst bit. And there's a test question on this. You have to understand how to place two programs into a block of memory that has some holes in it. And you'll say, well, I'll put A in hole 1 and B in hole 2, or I'll put A in hole 3 and B in hole 1, etc. So are there any questions about this? Okay. Can we do a practice problem? Sure. Just give me a second, set it up. I'm gonna put a whole bunch of, so I can move this up and see it better. And let's do another one. Okay, so I got this is program. Yeah, program A is running here, program B is running here, program C Linn here. Just clean this up a little bit. And I've got a hole. So hole 1 has 15K. Hole 2 has 5K. Hole 3 has 10K. And let's put one more program in. Okay, and we've got programs to be placed. So to place E, which needs 10K, F, which needs 3K. So first let's do it this way. First fit, it just goes down the holes sequentially, and the first one that it fits, it would put it in. So what would first fit do? Place it in which hole? Hole number 1, 2, or 3? Right. Okay, and when it does, it has 10K, right? And it still has hole 1, but how big is hole 1 now? 5K. So E would go in hole number 1. Where would F go? Hole number 1. Very good. Don't forget if you have anything left. Okay, that's first fit. You got it right. Let's try best fit. E in a 10K. The best fit means it's going to leave the smallest amount of space. So what would it go into? 3, leaving 0 holes. Right. Okay, then where would F go? 2, leaving the smallest one. Excellent. Okay, now we got those. Let's back it up and go worst fit. E would go where? Hole 1, right, leaving a 5K hole. And then where would the 3K go? $5K, leaving, no, it would go into, 3, you're right, I'm sorry. Leaving 5K, it would go into 3. Worst fit, right. Now, did that explain it? Okay. Yeah, this one is worth 3 points on the test. So you know it's got to be a multiple choice question. I didn't tell you that. I should have told you, like I told you all the time. There's five true, false, worth 1 point each. 5 multiple choice, 3 points each. 5 fill in the blanks, worth 5 points each, for a total of 45. 45. Plus, there's an extra credit problem, which I'll show you an example. Okay. And just to make sure that we're on the same thing, let's go back there and show you those 2 tests. They're 2 separate tests. The only way I could do extra credit was to have 2 different tests. One worth 45 points, one worth 0 points, and I would give you 5 points if you get them all correct. And I'll illustrate that. And I gave you an hour time limit on this and 3 hours time limit on the test. And it could take a whole hour to do the optional form. So that explains that. Okay, the next thing we looked at was virtual storage. And its management. Okay, so okay, I'll stop. Thanks, Karen. I didn't see that. Ken, let me read your question. For best fit, E to 3, but why would F to 1? Best fit? Did you say your best fit? Best fit leaves the smallest amount of holes remaining. So there would be no remaining. So E would go into 3 and on best fit, and F would go into 5, leaving a 2K hole. Yeah, F goes in the hole too on best fit. Okay. Okay, very good. Okay, virtual memory. One is the virtual format. Okay, that's a segment, right? Segment. Page within the segment. And displacement within the page. That's the typical form, and I gave you examples right here. I gave you virtual storage examples. So this question, there's a true or false question regarding the format. You'll tell me whether this is a valid format or not. Okay, that's one. Dynamic address translation. I spent quite a bit of time going over the dynamic address translation with you guys. And that's this one. It's worth 5 points. And it's converting a virtual address into a real address. Do we need to go over that one? Did you want to go over this again? Vega says no. Anybody else? Okay, we don't have to. Okay, that's that one. What? Oh, I got cap locks on. I still have cap locks on. What tables are needed for that to work? Okay, can you tell me what tables I'm going to need? The operating system has to build. Okay, we went over this before. No, not real. Well, it does it in real memory. That's true. It doesn't use virtual storage for the tables. It needs a segment map table which points to the page map tables for each segment. And the page map tables point to a page frame, and then the offset is added to that starting of that page frame to get the real address here in your page frames. You have to understand that, this mechanism. But tables. So let's go back to that. Segment map table, SNC, page map table, PNC, and that's for each segment. And then finally, the displacement within the page. Well, I should say the this should give you the page frame address. And then from that, you would add the displacement. That's how you do it. Okay? That's that one. So a table is dynamic address translation, and you'll have to show how the virtual address gets converted to a real address. And that's the one you didn't want to see, which was this one. But that's this problem. This problem is a multiple choice worth 3 points. So on this alone, you've got 1 point, 3 points, 5 points. A total of 9 points of the test is in this area. No, there's more. There's more than that. Shucks. 5. I forgot this one. There's another 5-pointer. And that is the replacement algorithms when no pre-frames are available. You have to pick a victim, remember that? I'm having a problem. Okay, what are the algorithms? Who? Principle of optimality. And what does that mean? Anybody? Replaces the page that will not be used the furthest time in the future. In other words, with all the pages that are being hit in the system, you want to replace the page that will not be used the furthest time in the future. That is what principle of optimality really is. Okay. There is not used recently. Concept. And it utilizes 2 bits on each page frame. the reference bit. And modify bit. And it replaces them 0, 0, 0 first, 0, 1 second, 1, 0 third, 1, 1 last, in that order. And then periodically, the reference bit is set, all reference bits, periodically, all reference bits are reset to 0. And then when it gets hit with a reference bit, it sets it back to 1. And that's how that one works. Then there's the concept of not used, not referenced recently. In other words, I have a timestamp each reference. Replace the oldest reference one. That's a slight improvement trying to implement this principle of optimality. This is really costly, a lot of hardware, you really can't do this, but the concept does exist. Then there's FIFO. You timestamp when the page was placed into memory. So when that page was placed, you replaced the oldest timestamp. And I have a sample of that. Matter of fact, I think I have a sample of all these. Let me see. Huh. Don't know why I have this graph reduction. I think I picked the wrong one when I was pulling them up. Well, let me continue. But I thought I had a sample of this. Least frequently used. There's a use count. Oh, this one's called least recently used. That's LRU, least recently used. Sorry, I didn't have the terminology right. Least recently is a timestamp. Least frequently is a use count. And you replace the page with the least number references. Okay, and with that there's most frequently used, which is you use a count, but you replace the page with the largest number of references. Don't ask me why. Gee. Why? Yeah, why? Gee. No, it's not that one. It's the clock policy one. It's kind of an implementation of least recently used with clock policy, and it's a round robin idea, round robin, checking the one bit. It's one bit. So when it checks it, it resets the bit from 1 to 0. When checking, if it's a 1, it resets it and moves the pointer to next block. It's not going to pick that. It wants to find a 0 that hasn't been referenced. So the idea is every time a block is referenced, this bit is set to 1. And then the clock policy guy sees a 1, sets it to 0, goes to the next one, gets the next one. And if they're all 1s, he sets them all to 0, then comes around and looks for the a 1. And this is the one that could be causing some issues because you might not find one. So you're going to need a current pointer with this concept. Current pointer required of where it's left off or something. Okay, and the last one is it was in my head and it went out. Working set. Give processes a starting number of frames. Choose replacement within that working set. And then occasionally you'll have to look to see if something is bigger. Okay, so now let's add up all of this stuff and see how many points chapters 8 and 9 are on the test. I got 1, 4, 9, 12, 17. 17 points are in this area on the test. Pretty important area. Okay, that's virtual storage and its stuff. Well, that includes, does that include this? No, that doesn't. This part was only, I think, worth about 5 points. Okay. So the next thing we looked at was files, and these were chapter 10, 11, 12. So file system, organization. Okay, you remember the different file organizations? There were 3. Sequential, anybody? Indexed, sequential, and direct. Okay, so with each of those different file organizations, you had an access method or API or something like that. So you would have sequential access method for sequential files, index access method for index files, or direct access method for basic direct access method. Either of those two are access methods that go with that. Okay. Then we looked at the disk organization. All right. And we looked at how to allocate blocks of the disk. And what were some of the methods we used? Contiguous, and we ran into issues here. Remember, in contiguous allocation, this is very similar to real memory. This guy up here. Fixed size partitions, and it would be variable size partitions for your blocks of data. And you have very similar issues. Okay. Then we had index, where you had an index pointing to a file. So you would have an index and a file, so an index block and a file block. And then we had the idea of block of file block mapping. With the file access table. And that's definitely on the test. Where the file access table has pointers in it. It would be something like this if this was 1 block, 2 blocks, 3 blocks, 4 blocks, 5 blocks, 6. It would be this block here, and then I have a pointer to that block, and then that block points to another block allocated. And this file allocation table represents a cluster on disk of what was allocated. I took you through that. It's in the notes and in the session. That's worth 3 points. There's also a 5-pointer, no, actually 10 pointers. There's 10 pointers in this area, so that's worth 10 points somewhere. Is that right? Let me think about it. Yeah. Then, more than 10. Then there's the protection, file protection concept. You could use a scheme like read, write, execute, read, write, execute, read, write, execute, read, write, execute, where the first one is the owner, the second one is the group, and the third one is other, or public. So that protection rights could be on files and directories. That's one scheme. And there's an access control list, or ACL, that it's an object, so it's an object that has owner and rights, what rights they have to that file, and has group as well. So this access control list keeps track of that. Protection, you're supposed to say protection. Okay. So I'm adding up the points on this guy, and it's got to be quite a bit because we used quite a bit up here. Okay, questions? Any questions? Okay, let's look at if I can find a sample of this. I thought I had it out, but I guess I don't. I'll go with the optional one. The optional one is, sample replacement algorithms. Here it is. So here's what the problem is going to look like. Process X had been executing. The last was in frame 4. Okay. It has 2 pages in memory, and it had a page fault. The OS must determine which page to replace for X's new page, using the information provided below. So we have the time it was entered, we have the last used time, we have the use count, and we have our clock policy with our pointer right here. So the least frequently used replacement strategy would replace what? Five. Correct. Good. Okay, what would least recently used replace? Six. Correct. It's this guy. Okay, what would FIFO replace? One is correct. This one, because that's the time it was entered. FIFO, first in, first out. Okay. Clock policy. Well, what would it do? It would flip this back to a 0, flip that to a 0, flip this 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 to a 0. This is 0. What would it pick? Guys? 5. Put 6. 5. Okay. Finally, is anybody confused over what I'm doing? This is what you're going to have to do on the test. Mega, how did I get 5? Okay, the way clock policy works is if this is a 1, it's not going to pick it, but it resets this to 0. So now you got to think that this is 0, okay? And then it moves down. That's not a 0, so it makes it 0. So in your mind, think that's 0. Come back up. This is not 0, and it sets it to 0. This is not 0, but it sets it to 0. This is not 0, but it sets it to 0. This is not 0, but it sets it to 0. And it looks at this, and this is now 0 because we had set it. That's correct, gang. That's correct. That's how it works. So, any other questions on any of these so far? Okay. Clock, a working set. Well, how many X is working at 2 and working in 4? So it's got 2 and 4. So if at the beginning it's when I load this page for process X, when I load this page for process X, it would get set. It would be 0, and it would be set to 0. And as soon as it referenced it, it would get set to 1. Okay. The other thing I should say is after it picks it, it moves the pointer to the next one to pick. It's not going to stay at that guy. It's going to move to the next guy. So it'll point to this guy to allow the page mapping or page memory system to come in and load a page for X here. All right? But it would also move down one to the next pointer because it just picked that guy. Okay. Working set. So I'm going to pick out of the 2 pages I have. Which would I pick? Two or 4? Why, Megan? Anybody? I mean, you're correct, but why? Why wouldn't I do 4? Oh, you're looking at the use count. Don't look at the use count. Because working set doesn't look at that. Because it doesn't exist. The use counts are only available in certain algorithms. Basically, least recently used. Same thing here. Use count isn't used in working set, but it's used in frequency set, least frequently used or most frequently used. Okay, it's in the reading up here. That's correct. Why would you, if the last access was in page 4, in other words, this page frame, what it did was it branched to a page, like it might be calling a subroutine that's not in memory. So we have to load that subroutine, but what happens when we come back? Well, we're going to have to load it again. So why would you pick the one that was last referenced? You would pick one that wasn't. Okay? In this scheme. Now you could have other rules too. I mean, you could have other sets of rules going on. But I didn't give you any additional rules. Okay. So this would be 2. Recent. Recent means last used. Recent. So we're looking at that time, and that's why 6 was chosen. Whenever you have least recently used, you're having a timestamp. And you're looking at the one that hasn't been used recently. And that's pretty close. This one, least recently used, concept is pretty close to poo. Poo goes the other way. This says what's happened in the past. Poo, principle of ophthalmology, says what's going to happen in the future, which we won't know, because we can't predict how programs are going to run with if statements in them. Theoretically, yeah. Theoretically, that's right. Okay, so we did this one. Let me go back to here. Any questions on the file stuff? Okay, then I'm going to move on to the optional problem. I really like this problem. Okay. I think I've got it posted out there. Let me check. If I don't, I'll post it on Canvas. Yeah, sample this guy. It's out there. And I have two pages. I got the solution, but I wanted to take you through it. And then I'll check to see if I did the solution right. So here's how it, and this is why you might need an hour to do this. Assume you have a multi-programming system, 1 CPU, and 2 I/O processors. That's in case you're on I/O. Both of these programs are on I/O. They could be on I/O at the same time. Okay? They can't be on the CPU at the same time because only got 1 CPU. Assume only 2 processes will run on the system simultaneously. The use of CPU and I/O by each process is shown below. 10 CPU units, 7 I/O. And we're going to assume that the 7 and the 10 units, each of these are the same unit size. We know that's not true in reality. First time 0, so we're going to start at 0. And the operating system is going to start. So we're going to show the operating system executing. He also assumes the operating system requires 2 cycles each time. We know that's not going to be reality, but it's close enough for this kind of problem. It's going to be difficult enough to figure it out. Also, no other processes will enter, so we don't have to worry about that until all processes are finished. Quantum is 5 units. So we're going to give a timeout with this at 5 units. And assume service request precedes timeouts. In other words, because they're exactly 5 units, I've got the CPU. When it ends at CPU, it's calling for a timeout, all right, in this case. So we're not going to do a CPU timeout. We're going to do a service request at the end of this last 5 units. And that's what this means. Assume the service request precedes the units of running out. And what we're going to ask is, what time unit will each process finish? Assume first come, first serve in the ready state. Dispatcher uses round robin without priorities. That's what I was trying to say here. And the initial order is A, B. And you fill in the chart to figure it out. So here's how you're going to fill in the chart. The OS starts up. So it's going to go 1, 2 units. And the vertical bar is the end of the unit. So dashes, the horizontal line is the CPU. So the CPU does 2 units. And it ends at the end of that unit. And its role is to, call the dispatcher. The dispatcher finds out A is in the ready list. So we need to have another list going on here. So let me do it this way. So I'm going to start A up. So in my ready list I have still B. I don't have any blocked, but A is running, and that's what this 2 units of OS did. So if we come up here and put A there, that's the first unit of A right here. And it runs for 4 more units. 1, 2, 3, 4. And that takes a total of 5 units right here. Or I guess we could show it starting here. Let me do that. It might make it more sense to not count this start as a unit. So count that. Yeah, that might make more sense. So we start, it goes 1, 2, 3, 4, 5, and we time them out at 5, which means that the operating system is going to be coming in here for 2 units. 1, 2. Okay? That's what's going to happen. And then A is not running. We're going to assign B, but we're going to put A back in the ready list because it timed out, and we're using round robin. So we're going to start up B. So let's start up B. And we go 1, 2, 3, 4. But the 5th one, we have a service request right here. We have a service request. So the operating system is going to come in and handle that request right here. And it's going to take 2 units to do that. And it's going to take B from running and put it blocked. We keep track of that. And we're going to start up A because it still needs something. So we'll put A as executing. And now, oh, we need to start the I/O for B. We didn't do that. So right here, we need to start the I/O. Whoops. Start the I/O device. And I/O devices, we're going to use a zigzag line of 3. So it's going to be a tilde. And it's going to interrupt us after 3 units. Okay, so we have to make a note of that we're going to get an interrupt right at 19, unit 19. Are you guys following this okay so far? Pretty confusing.
Mm-hmm.
A bit confusing. Okay, you'll rewatch, but I'll keep going and maybe it'll come to you, okay, as to what's happening. All right. Well, we know we're going to get an interrupt here when the I/O completes. But we started A right here. So the CPU was actually started here as well for program A. But it's going to go for 5 units, but watch what happens. 1, 2, it only gets 3 units. It only gets 3 units because an interrupt occurred right here, this I/O completion interrupt. And the operating system came in to handle that. So the operating system is going to come in here for 2 units to handle that completion. All right? So we're going to keep A running because we're not going to preempt it because there's no priorities. We're not going to preempt it. So this goes in the held state. Remember that state? We hold it for a bit, so it's held for a bit, and we take B out of being blocked and put it in ready to go because its I/O is complete. All of that is going on in these 2 operating system units. And then we restart A with the smaller quantum. It had 3, and it still needed to have a quantum of 5, so we're going to start it up for 2 units. Okay, so right here, we'll start it up, get 1 and 2. Now, let's count the units to make sure we got all 5. 1, 2, 3, 4, 5. It got all of its 5 units, but it's requesting service right here. So once again, the operating system is going to come in right here and handle that service. Okay, so I should have said when we were here, we unheld A, and it's still running. We set them to run. And it got its two more units and request service. So here we're requesting service. A is going to move from running to blocked. We're going to put B running. So we're going to change the queues. B is going to be running. We do a start I/O for A right here. We start up the I/O that it's requesting, and it's going to take 7 units. So let's count off 7. And I'm going to use squiggly lines for the I/O. 1, 2, 3, 4, 5, 6, and it's going to come back on the 7th unit. So 7 units later is going to be an interrupt from the I/O device. But I also started up B right here. So B is actually executing, and it goes for, looks like 10 CPU units. So it's going to go 1, 2, 3, 4, 5. 5. So there's its 5, and it's going to time out. All right. But the operating system's going to come in right here. I'm going to time out and handle the timeout, but it's going to get interrupted right before it does anything. So what happened in this timeout was it took B, put it off, put it back as blocked, and it went to restart B, right? It was going to restart B right here. So let's note that it's going to restart B because there's no other processes running. Oops. So it restarts B, but before it could execute B right here, it had to handle A's interrupt. So we're right back in the operating system for 2 more units, handling the A coming back. So we put it in the ready state, and we had assigned B the processor, so B would be running its last 5 units right here, 1, 2, 3, 4, and it completes. And I use a right bracket for completion, right bracket for completion, which means it's going to come back to the operating system at this point. And for 2 units, the operating system's going to do this. It's going to get rid of B, get rid of that whole process, mark it terminated, and it's going to put A back in, executing. So we'll get A executing again, right, starting from that spot. So it's going to start here and go for 5 units, and it completes. And that completion is going to signal the operating system to come in, and there's nothing to do at this point. So it goes into an idle state, waiting for an interrupt. And the answers are going to be this. When does A complete? What unit did A complete at? What unit? What do you mean that's 2, not 3? I'm sorry, which one? 46. Yeah, it completed at 46 is correct. When did B complete? Yes. And when did the operating system run out of things to do? Okay. How many units did the operating system use? These are all questions that are on the test. No. How many cycles? How many units did it use to service all of this stuff? Yeah, you just count 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2 is, Albert's correct. 9 times 2 is 18. It took 18 units. Well, let's see if we were right. Looks like I'm using different schemes here on this one. This looks right. I wonder how it could be off. This is 39. It's hard to read, but this is 46 right here. And it took 1, 2, 3, 4, 5, 6, 7, 8, 9, the exact same 18 units. So this is exactly the same. The only difference is I didn't have a beginning like I do here. It's a little clearer to me. It's clearer this way. But if you don't want to use that, you can use this concept. It doesn't matter how you reference it. But the answer is this finished at A finished at 46 units, and B finished at 39 units. And then the OS had 18 units of work. Okay, and there's 2 other questions that I have. So this would be worth 1 point. This would be worth 1 point. This would be worth 1 point. And there's 2 other questions that I'm not going to tell you now. Would be worth 1 point each. Okay, but that's the optional problem. If you attempt it, and I see that you're attempting it, you'll probably get 1 point, even though you don't finish it. All right? Your problem will be a little more complicated than this, meaning that I could change it to 2 processors. So you have 2 processors running, and each one of these would be, the operating system would be running on that. I don't think I'll do that, but I could. And I could add 2 other processes. I'd be more likely to add 2 other processes. Okay. But is this better now, Karen and Megan? Is it clear what I'm doing? Good. Yeah, this is the same diagram. The only difference is I counted this as not counting on a unit, and I started this way. I could have, I guess, put the dash or whatever it is here. I didn't do that. Okay. The reason I like this problem, because if you can understand this, you really can understand how operating systems work. Without, you know, going into the code. What do you mean? You won't see. You can use any scheme you want. Okay? Yeah, doesn't matter to me. As long as I can understand what you're doing. This scheme is fine. If you use this scheme, it's fine. Okay? Might be better, I don't know. I only use the starting because it just lined up nicely. I could have used the other scheme. I mean, if you want to see the other scheme, I can change these. Yes, this is Notepad. So yes, I'm using a fixed size font. And you should use a fixed size font. If you don't, you'll be in trouble. And I believe on the test, I tell you to copy this and paste it into it, because I think it's pre-formatted for fixed size font. If it's not, here's what I would do, Karen. I would just take the whole test question, copy it, and paste it into Notepad, and then do it in Notepad, and then just copy the answer part back and into the answer. That's what I would do. Okay? Yeah, that's right. Well, that's the optional. That's why it would take an hour to do. Think it through. And typically what I do, I'll tell you, if you're close, right, you may have screwed up on something. If you're close to it, like in this case, if you have 45 or 47, I would probably account that. Or if you had 38 or 40, you made one little mistake, I'd probably give you credit for that. Okay? But there are 5 questions on the test. And you're seeing 3 of them right here. I'm going to surprise you with the other 2.
Isn't that exciting?
Isn't that exciting? My wife said. Okay, what else do we need to talk about? Because we're almost out of time. And I thought we'd be done. I did that one already, Mega. You'll have to pick it up in the first 5 minutes. I did that right away. You know, on the recording. I can give you a hint, though. It's in this. The answer's in here. Okay. Any other questions? Oh, I know what I wanted to do. Yeah, I wanted to talk about that, Kang. Oh, yeah, they will. I forgot that. Thank you for reminding me. I just forgot that what would we call those? Disk access strategies. We had FIFO, first come, first serve. We had scan. We we had C-scan and look. And I forgot the other one. C-look, thank you. Yeah, I have one just like on the homeworks. Remember on the homeworks? Shortest seat time first, yeah. Where would that be? Oh, yeah. Wouldn't be these. Thank you, Albert. Yeah, I believe this is a 5-pointer, so you're going to have to do some addition. I'll give you, it'll be just like the problem in the homeworks, except I'll change the numbers. You know, the number, where to go and that kind of stuff. I was going to try and get to Canvas. Let's see, where was that? Is it in 11? I think it was in 11. Might have been in 12. Just don't remember. Yeah, it was in 12. And then I wanted to go to Kang's question about the final exam questions. I tried answering them earlier. I don't know if you were on when I was going through that. Yeah, this is the one. No, this isn't the one. It must be 10. Must have been 10. Yeah. Yeah, it's this one. Yeah, this problem. I can't remember if it's worth 5 points or 3 points, but it's on the test. Except I'll change these numbers that you see. And I'm not going to do all, I'm only going to do 5, so it must be a 5-pointer. Obviously, I'm not going to do one of those. Okay. Let's go to discussions. So the idea is you would reply here. You would reply here to this main topic. If you wanted to reply to a specific question that somebody gave, you would reply to that, like I did. And I told them either way is okay. Before I let you guys go on that, I need to confirm that in my mind. So let me go to something to see. I'll go to class in a summer class. Yeah, that's it. Okay, I'm gonna answer your question now. It's a good question, Kay. Don't use the A, B, C, D, E. Just use the sample. Okay, I'll put out an email to everybody on that. That when I did this model, I should have taken those off. Okay? Any questions on that? So I'll send an email out that I can't edit this now. It's too late. You only get a half hour to edit it. Well, let me look. I can edit it. Let me see. That might be. I don't want people confused. Let's see if that works. Okay, I think you got it. Thank you, Kang, for noting that. Yeah, I could do that, but I didn't want to do that. I'd rather have you guys working off of the one I'm working on. So we got it. Yeah, once again, this is the first time I'm using Canvas for this class, so I've got little tweaks to do before I 100% on this product. All right. I wish you well on the test. I've covered almost everything that's on the test. I'm going to save this file, and I'm going to repost it on Canvas as our agenda. But it has almost everything that we've talked about. So, any last-minute questions? Well, just don't wait too long to do the test, right, guys? You gotta, you know, I wouldn't wait until 11 o'clock to do this test because it's going to close at midnight on Sunday. And whatever you've done, if you're working it, it closes. So give yourself time to do it. Do it. Start it tomorrow or Saturday or something. Okay? All right. If there's any kind of issue along, email me at Linn Jr. Arthur at Foothill FHDA. Because I look at that more often than I look at Canvas. All right. You have a great weekend. I'm looking forward to seeing how you guys do on the test. Thank you. Thank you all for participating. I'm going to stop desktop sharing. Sure, Mega, go ahead. You have a final project in my class or some other class? Do you want me to turn off recording? All right, I'll stop recording this. Good night, everybody.